we're able to calculate the orbits of the asteroids. But one problem is that they are very small and their orbits are very easy to move around. So we can see they're going to miss us, but then we realize, oh wait, the orbit shifts. If it misses Earth near as a nearby sort of thing, then it's going to Earth's gravity is going to shift the orbit of the asteroid. Then we got to recalculate what it's going to do. If it passes by the moon's gravity will shift the orbit a little bit. If it passes by Mars or Venus or Jupiter, those planets' gravity will shift. Well, even if it doesn't pass very close by, the orbits will shift even from a great distance. In physics, solving orbital dynamics, what we call astrodynamics, is exceedingly difficult in the solar system. Something called the three-body problem, in which you've got the sun, you've got the object you're trying to figure out the orbit of, and then you've got something else out there perturbing the orbit. And so in graduate school, this was a big deal, was how to handle perturbations in these sort of calculations. And it's very, very difficult and not really able to be done precisely. So that means that there's a certain amount of uncertainty in orbits, and the farther you go into the future, the less certain you are of where the asteroid is going to be. At some point in the very distant future, then what we find is that there's just simply no way that you're going to be able to actually calculate what the orbit is going to be. Okay, so, but having said that, besides gravity, light can affect things. So, for example, we have light affecting things, and so we've got something called the Yarkovsky Effect, named after a physicist that studied it. Now, remember, we said that light has pressure. Light pushes on things. So just the sunlight hitting the asteroid pushes on it. That will shift the orbit. But another thing that happens is that as the object is turning, then one side is warming up, okay? And so as it's turning, one side of the asteroid is warmer than the other side. That means it's giving off light with a shorter wavelength than light on the cool side. Now, one of the things we discover is the momentum of light is closely related to the wavelength of light. The shorter wavelength, the higher frequency light, has more momentum than the longer wavelength, lower frequency light. And so that means, in physics, change of momentum is a force. That means if one side is short wavelength, the other side's long wavelength, there's going to be a force pushing the asteroid that way. Okay. So that would mean if the asteroid is going around the sun, as shown, it had to push forward on it, and so that's going to make the asteroid spin outwards like that. Okay. On the other hand, if the asteroid were rotating in the other direction, it would gradually spiral inwards, closer to the sun. And so this effect does, in fact, change the orbit of the asteroid. It has been observed. We've seen asteroids whose orbit has gradually shifted over time due to the rotation. The faster the asteroid rotates, the less chance the cool side gets to cool off, and so the less an effect this is going to be. The slower it rotates, the bigger the effect. Again, this is something that we have observed happening with asteroids. It's actually something that's kind of useful. If you have an asteroid that's coming towards Earth and you know it's on impact with Earth, one of the things that you sometimes see in science fiction or Hollywood idea is, well, go blow it up. Well, these things are so big you can't just go blow it up. The other problem is, even if you blow it up, then you have a cloud of little things here that nothing else is nearby, so gravity pulls it all back together, and now you have an asteroid again. And so you don't just go blow it up. A better solution is nudging it somehow, and NASA has talked about possibly nudging it by having something, bump into it, intentionally hit it, and maybe nudge it off course. Another idea is to maybe launch a big rocket to the back end of it and push on it to change the speed it up or slow it down to make it spiral inward or out. Okay, that's very difficult to do as well. A low-tech solution is to paint it. Now, I don't mean you send a bunch of astronauts up there with spray paint or something to paint the asteroid. What you do is you send an unmanned spacecraft up there with like chalk dust or powder, light-colored powder, because most asteroids are dark in color. And so what you do is you have the spacecraft get close, and then it blows up and just covers the asteroid in this white powder. That would change the characteristics. The white would reflect heat from the sun. It would not heat up as much. It would not radiate as much. And so what would happen is that would change the Yarkovsky effect, which would change the shift in the orbit. Now, if you change it enough, that could actually cause this thing to miss Earth. So this is something that's been considered as one of the mitigating strategies for an impact. Another Yarkovsky-related effect, the Yarkovsky Radzivsky-Paddock effect, or YORP for short, because no one wants to say all those words, okay, all those names. And that is if you have an asteroid that's oblong in shape. So not all asteroids are going to be spherical. Some of them are going to be kind of oblong in shape. And so if they're oblong in shape, the Yarkovsky type effect will push more on one side than the other side. So as it's rotating, what's going to happen is it's going to exert a torque on it and change the speed of rotation, either speed it up or slow it down. And so these are two effects that can happen to asteroids just due to light pressure. Then you add the third effect of just the sunlight hitting it, shifting the orbit. So these things are all very, very difficult to predict what's going to happen in the future. Not impossible, but difficult to predict. For the short term, we can do it. The farther we go into the future, the more difficult it is to protect, and the more uncertainty it is from the predictions. Ultimately, if you try to figure out what these things are going to be doing in a million years, you're probably hopeless because the uncertainty is going to be bigger than the orbit, at least with the current state of mathematics.